All right, sorry for the delay. Yes, this is Visual-SLAM and Dynamic Scene Understanding for Autonomous Systems, and it's a joint work. A lot of students contributed, in particular Lou, Felix, Wei-Rong, Ganlin, and Simon, and then two external collaborators, Andrea and Christian. Maybe a few words, you mentioned it already, we are based in Munich, and we're engaged in a variety of activities. I'm one of the directors of the Munich unit of ELIS, the ELIS network, and I'm also engaged as one of the directors of the Munich Center for Machine Learning. This is one of actually of 5 AI competence centers across Germany that are permanently funded, and this is actually outdated, we're now 80 professors from both universities, so it's actually the biggest AI competence center in Germany, just because Munich is obviously a big hub with a lot of activities. And we have different focus areas, so this covers really all areas of AI, from mathematical and algorithmic foundations, perception, vision, natural language processing, robotics, etc., but also a lot of domain-specific machine learning in the life sciences, in medicine, in Earth observation, etc. And so it's really the whole spectrum, also social sciences, for example. We try to really cover all areas of AI. My own beginnings, I decided to go back a little bit. We started with robotics and autonomous systems very early on. This is footage that we recorded in 2005. We started to put in cameras in cars, recording what happens in front of the car in order to develop algorithms such as this one, scene flow algorithms, that would allow you to capture 3D structure and movement. And this is obviously kind of the first steps that we took in the direction of driver assistance and autonomous driving. We also started early on with drones. This is a picture in 2007 in my office back in Bonn, and this is a drone that we actually assembled ourselves. At that time, you could not buy them commercially. And so we had to really 3D print the frame, we had to put the rotors, everything manually, and then we added cameras and started to develop autonomous flight. Here's one example. This is 2012 IROS, where we showed one of the first autonomously flying drones that used purely the onboard sensors to localize itself. And so this was my beginning, since SLAM started with us running PTAM essentially on the drone. PTAM is a very powerful tracking and mapping from Klein and Moray, the stuff that also went into the HoloLens later on. So really amazing tool, and it enables you to localize yourself in 3D space, but typically, you know, the title of PTAM already says it, it's for small desktop environments, and if you want these systems to go further to map larger scales, it wasn't accurate enough, and that's how we got into SLAM. And so you see, you can demo it in many ways. Here's a demo where the system is just asked to hover in space. And then you can see how robust it is. You can push it away, you can cover the sensors, etc. And so this was kind of 3D computer vision, real-time 3D computer vision in action to enable autonomous systems. And there were all sorts of papers we wrote over the years: obstacle avoidance, path planning, trajectory re-estimation. Here, for example, you have a drone that has a limited horizon view, and then some obstacle comes into the way, and so in real time you need to update the trajectory to keep your direction but somehow avoid the obstacle. And a lot of this went into technology transfer and startups, for example, based on all of this stuff. Adam Bry came from MIT to see what we were doing, and he was sitting in my office. We showed him all these demos, and he said, "I really love this. I'd like to build a startup on this. Will you help me?" And I said, "Sure, I'm happy to serve as an advisor," and so I did. And by now I was surprised myself, they fared fairly well. So this is now the largest drone manufacturer in America with a multi-billion-dollar valuation. And so that sparked, obviously, my excitement for startups to see that there is a way to bring these technologies into the world. And so this is another thing that I'm pursuing increasingly now. But what I want to talk about today is really what is necessary for these autonomous systems is the capability to capture the complex dynamic world that we live in. And I think especially for example, things like self-driving cars, to date, most self-driving cars differ from human drivers in that they don't have the same kind of level of anticipation and understanding of how my fellow participants in traffic typically behave. What are they going to do? And it's often complex negotiations. If you want to find yourself into an intersection and there's massive traffic, most self-driving cars I know, they will just stall and wait till the intersection is clear. That might work in Germany, it might work on the West Coast, but it will not work in Mumbai, and it will not work in many other parts of the world. Sicily, for example, I know I don't drive in Sicily because, you know, yeah. Because I don't have the knowledge of how people typically behave. They just behave slightly differently from Germany. What can I say? It's, yeah. And I think the key is we really need to devise techniques to understand the 3D world. And so I'll talk about first capturing the static world, but then also capturing the dynamics in the world. Static world, this is SLAM, and I'm very happy to say that together with many contributors, we were able to bring out this SLAM handbook, and a lot of contributors are sitting here in the audience. And so this was a huge effort. This is actually a book that is actually 3 books. There is the foundations, there is SLAM in practice, and then the third part, SLAM to spatial AI. And so we're very grateful to all the collaborators who made this happen, who made this work. And if you're interested, the PDF version is online. So this is trying to cover the last, you know, the foundations, but also what happened in the last 20 or 30 years in this area of SLAM. Because it's a very active area, and even when, you know, devising the book, we realized we cannot really cover everything. We try to cover everything, but, you know, there is a new paper out coming out on a weekly basis, and so we really try to get into a lot of, you know, things like dynamic SLAM, deformable SLAM, learning-based SLAM, LiDAR SLAM, legged odometry, things like that, visual-inertial, sensor fusion. A lot of these topics are all covered in this book, so this, for anyone interested in SLAM, this might be a good reference to read up on certain things. SLAM is a long-standing problem. This is one of the pioneers, Erwin Kruppa, and back in 2013, so this shows you how old this was a discussion, because when we discussed among the editors SLAM, you know, some of my robotics fellows said SLAM was developed in the mid-90s, 95 or something. And from a computer vision perspective, that's just not true, right? There is, you know, centuries of research, and if you want to know more about the history, there are people like Peter Sturm who spend a lot of time digging into the histories, finding that, for example, reconstruction from photographs is almost as old as photography itself, right? Just a few decades after photography was invented, people started coming up with ways of measuring the 3D world from photos. And what I found in my own studies is that TU Munich is one of the birthplaces of photogrammetry. And researchers like Sebastian Finsterwalder, who is often called the father of analytical photogrammetry, they were professors at TU Munich more than 100 years ago, devising technique. And what did they do? They liked the Alps, much like people here in Grenoble. They went into the Alps. So they were both professors at TUM, but also mountaineers. And so they would go in the Alps with massive, you know, photography equipment and try to map the glaciers in the Alps. Maybe to monitor climate change. I don't know exactly why they set out to do these things, but it was very tedious because this was all well before the age of computers, right? 1913, there were no computers around. So even for me today, looking at this, I think, why would anyone work on this problem if you didn't have a computer to actually solve it? Well, they came up with analytical solutions showing that if you have 5 corresponding points, you can solve the problem. And that led then much later to computer vision, 3D computer vision algorithms this is a lot of pioneering works on real-time Visual-SLAM by Hailin Jin, Paolo Favros, Stefano Suato, Andy Davis, and many people who laid the foundations of real-time Visual-SLAM. So this is really amazing stuff, and a lot of this really follows very closely in Krupa's footsteps. What we advocated over the last a little more than a decade is so-called direct methods, methods that don't take points, extract points and features, but go straight from the raw sensory data to a reconstruction of 3D motion and camera motion and 3D structure. Here's one work, probably my most influential paper is LSD-SLAM, a work done by Jacob Engel and collaborators. Here's the moving camera, here's the 3D reconstruction, and this, I think, was possibly the first work that was able to capture 3D in real time at massive scale on a simple laptop CPU. So you could really walk around outside, just equipped with a camera and a laptop, and it would reconstruct like this. There was no GPU, so it just ran on a laptop, even on smartphones at the time. And we were very fortunate to receive the Test of Time Award last year at ECCV for this work. So that is something, over the years as a researcher, you get all sorts of awards, but this one is one that I'm really proud of, I can say, because it is a work that is very central to the research I've done with my team. And it's also things that ultimately are going into projects like the ARIA project at Meta, which is actually led by Jacob Engel. This is the follow-up to LSD-SLAM, a technique called direct sparse odometry. Many of you will know it. So equipped again with just one gray value camera, we can walk through the subway station here, back out on the other side. And this shows you at what spatial scale we were able to reconstruct back in 2017 when the work came out. We were able to reconstruct at very large scale and fairly high precision. Obviously, it's not perfect, so if you track cameras over thousands of frames, you'll accumulate a drift, and we wanted to showcase how big is the drift. This bicycle is reconstructed twice, so it's like 2 or 3 meters on a distance of hundreds of meters. And so we went further into evaluating this, creating data sets, and then showing that it actually works quite well. So this is evaluation on this data set where there's 500 sequences, and what we plot on the x-axis is the drift in translation, rotation, and scale, and on the y-axis the number of sequences. And this is a comparison to a technique that even today is often still considered a state-of-the-art SLAM method, a very powerful one, ORB-SLAM, from a team in Zaragoza. So this is many of you will know ORB-SLAM. A lot of people use it. We like to use it. It's really an amazing tool. But even here, we could show that compared to ORB-SLAM, we get a dramatic boost in precision. So if you say, what is the error on the best 300 sequences, ORB-SLAM has an error of around 6. We have an error of around 1. So, this is not a 5% improvement on the baseline, but this is almost an order of magnitude more accurate. And similarly, if you say, I want a maximum error of 2, how many of the 500 sequences can I track with that error? ORB-SLAM can track 100, we can track 400. So it's also a significant boost in robustness in a way. Here's a more recent work where we combined a DSO with an inertial sensor, a technique called DMVIO, and I don't want to go into technicalities. It's a fairly sophisticated technique, just combining a camera and IMU. And you see we go through a slide here. If you've never visited us, do come visit in Munich. We have a slide that goes 3 floors down, from the 3rd floor down to the basement. And you can see inside the slide, it's fairly dark, and still this visual-inertial system can track with very high precision. Through the slide, up 3 flights of stairs, down 3 flights of stairs, back into the corridor. And there is an offset, right? So the walls, you see there's like a ½ meter drift that we aggregated over time. But given the distance that we traveled through the tube and up and down the staircases, it's actually extremely precise and robust. And the nice thing is, this is not a learning-based approach. So you can take the exact same approach and put it in the car. You don't need to modify anything, and it will map and track. Right? There's no domain shift, no domain drift. This is just based on very basic principles. But I said it's not learning based. Obviously, we should embrace the developments. And when in 2012 the deep networks came through on ImageNet, right? This was obviously, an important breakthrough. And it raises, the question, how can we deploy deep networks beyond image classification? I should say, I know image classification is an important problem, and many people have worked on it, but it's never been my most fascinating topic in computer vision. You get an image, whether this is an airplane, a cat, or a dog. I don't know, I've never really cared so much about this, and I can imagine that you can devise machines that can figure it out, but And this was a massive breakthrough, no doubt, but for me there are other challenges more in 3D vision that I found more fascinating. And so from very early on, we looked at how else can we deploy deep networks. For example, in 2015, we showed that you can massively accelerate MRI scanning with a deep learning enhanced approach that we called Q-space deep learning. And I see nowadays in medical, tons of people are pursuing exactly that line of research. But we were very early in 2015 showing that you can actually accelerate it by an order of magnitude. So the patient can spend 10 times less time in the scanner and you get the same quality result. We also showed that you can tackle completely different problems from classification, that you can do optical flow estimation, training a neural network that directly predicts the flow, just from training data, right? And I do believe that pretty much all current state-of-the-art optical flow algorithms essentially go back to this paper that we called FlowNet. And then we went on. This is a follow-up work where we said we can extend it, not just predicting flow, but also stereo and scene flow. And we provided data sets to train networks to predict all of these low-level features, if you will. And then we went very far beyond computer vision. This is 2016. We showed that you can do protein prediction with deep networks. And I believe that was the first work that advocated a deep network to directly predict the protein structure. And so this is an important challenge in chemistry, where you're given an amino acid sequence and you want to know what is the 3D structure of the protein that it encodes. How did we solve it? We said take a data set of sequences with known structure and do what's called a multi-sequence alignment, aligning these sequences with all of these, identify the pairwise variance of mutations, compute what's called the co-evolution statistics, and then the core idea was to train a deep network to predict straight from the raw co-evolution statistics the contact map that encodes the 3D structure. If that sounds familiar to you, it should. This is a precursor, essentially a blueprint for Google AlphaFold. And if you have followed the news, you will know that they ended up getting the Nobel Prize for this. What's very unfortunate for us is they never cited our paper. And it's crystal clear the Nobel Committee was not aware of our paper either. And so this is somehow the unfortunate side of science, that sometimes it taught me that you don't have to do science only and research and publish, but you have to do PR and you have to, make advertisement for what you do. So if you're a young researcher and you want to pursue an academic career, we discussed it with Andrea. Andrea said he's not on social media. That can be a mistake. If you don't do PR for what you do, so think about it, right? All right, never mind. So coming back to 3D computer vision, how can we deploy deep networks for SLAM? This is something that mesmerized me for a while. And it actually, if you look at history, it took a while before people started looking into it, around 2017. And what we did, we built up on a network that could predict depths, much like what we did in 2016, depth prediction. This is another network by Kuznetsov and collaborators. We provided a better network. We call it it StackNet, that gave you more crisp depth predictions. I would say by now this is far outdated by all the latest depth prediction networks that we've had. But for us, the focus was not so much on the depth prediction itself, but how can we use this for SLAM? And so the idea we had in 2 papers in 18 and 20 is that we train a deep network given 2 consecutive images to give us the depths, to give us the relative camera motion between these, and to give us some notion of uncertainty. Uncertainty basically means in SLAM you want to know, you basically build on brightness consistency, right? And as you know, there are areas in this world that are Lambertian, where the brightness is preserved over time. When you move around, you see the same brightness. And then there are non-Lambertian areas like metallic, shiny structures, glass structures. And then obviously, as a SLAM system, you shouldn't impose brightness consistency for these areas because they will typically not preserve their brightness when you move. Right? And then if you have a world that is not perfectly Lambertian, the question is, how do you model that? You can try to model the reflectance properties of the world, right? The translucency of glass, the metallic reflections, you name it, right? But this is going to be very tough to do in a real-time SLAM system. And in the end, you don't care about the reflectance properties. All you care about is tracking the camera movement, right? And so what we did here is we said, let's ignore these. Let's train a network to tell us which areas we can rely on and which ones we cannot. And so we feed all that into a SLAM pipeline. Maybe I should clarify how it's fed in as in the front end, as an initialization using so-called factor graphs. And then it's also fed in the back end where we have additional terms in our loss function that say, find a reconstruction of the world that is compatible with what the deep network predicted for every keyframe. And these predictions stabilize the system massively. They lead to a boost in precision and a boost in robustness. And in particular, what they lead to is the ability to reconstruct large-scale scenes from just one camera without any scale drift, because monocular systems drift in scale. You know, and for decades I told generations of students in all my classes, I told them you cannot determine the scale of the world from a single moving camera. And then my students did it, right? And then I realized, oh, I was wrong, right? You can if you know the world that you're going through, right? And these networks, they know. So these depth predictions are metric. They are in units, right?
But Daniel, when you have a camera that's at a fixed height above ground, it's an easy problem. It's the general problem.
Yeah. So obviously the general problem, and I'm saying you cannot always do it. You're right. Yeah. I mean, for example, you know, if you took this approach into a Lego world, then it would reconstruct it perfectly, but obviously at the wrong scale, right? It learns, you know, what size the objects are, right? And if the Mercedes in front of you is you know, a Matchbox Mercedes, then it will not be able to see that, right? Obviously. So it's kind of trained in a known world, and that's where it works. But we found even if you train it in self-driving and you take it elsewhere, it still works surprisingly well. But I wouldn't fully trust it if you go through the forest, let's say, right? Maybe one more thing, event cameras. I think this is a very promising sensor. It's been around since 2006, roughly. And I think there is potential in this sensor, and so I want to use this opportunity to advocate this sensor. For those who don't know, an event sensor is a little bit, it's also called neuromorphic sensor, or there's different names for it, dynamic vision sensor, so different terms. But basically, in comparison to a standard frame camera, the event camera only transmits information if the brightness changes. So if you have this example of the rotating dots that a lot of people present in this context, it basically triggers events only if the brightness changes. And a nice feature, there are several nice features of these sensors, but one of them is that it uses the bandwidth more efficiently, in the sense that you only trigger events if something happens, whereas here you would communicate a color even though it's the same color that you had before, right? And so in principle, this makes sense. And that allows you to get essentially, you know, they say infinite temporal resolution, but let's say very high temporal resolution, because these events can have any timestamp. They're not limited to whatever 30 or 60 frames a second. So especially for high-speed robotic systems like drones, this may be a very promising sensor. There's been a lot of research on SLAM for event sensors. I do believe, I may be wrong, but I do believe that this, from my literature study, our work is the first event-based SLAM system back in 2014, ICRA. How did that come about? Jörg Konrad is the guy. He came from the INI labs in Zurich, where they invented the event sensor, and he brought an event sensor from Zurich. And then we joined, he met me, and then obviously if you take an event sensor guy and put him together with a SLAM guy, then surprise, surprise, you get event-based SLAM, right? It's a fairly obvious thing to do. But I should say this was, we say, a depth augmented vision sensor, so we combined this event sensor with a depth sensing camera. And I was not fully happy with that work, honestly, because, you know, the event sensor has infinite temporal resolution, but we combine it with a frame camera that has limited temporal resolution. And that is, in a way, an event sensor on crutches, if you will. And unfortunately, you know, I looked, a lot of amazing work appeared in the wake. Andy Davison, Stefan Leutenegger, Han-Mei Kim did this really nice work on event time tracking with an event camera. Then also Davide Scaramuzza, many others did great papers. But many of them are a little bit similar, like this one. You see Ultimate SLAM combining events, images, and IMU. And this, the title sounds nice, but you know, if you dig deeper, you can ask, why do we need to combine these sensors? Can we not just go with a pure event sensor? Because once you combine them, you typically lose the benefit. You have something with infinite temporal resolution, then you add a frame camera, but that only generates 30 frames a second, and then you're often back down to something that runs at 30 frames a second. And so what we looked at and what we found is if you just use a monocular event-only system, then existing approaches were not very accurate. And so last year we went back to the drawing board and we published a work that is called DEVO, Deep Event Visual Odometry. And so this is a deep learning based approach where we basically extract patches of events, and we have a patch selector, and then we have a differentiable bundle adjustment that basically is like a bundle adjustment but unrolled into a neural network. And then we train it in a supervised way using flow. So we have the camera movement, we have the inverse steps. From that we can determine the ground truth displacement that we should see, and then we can impose that as a loss function for training. And we found that this works extremely well. And here's examples where you see the red is the ground truth movement and blue is the DEVO. And there are two aspects that you can see already in these experiments. The first one is it works really well. Also, it has this high dynamic range capacity. So the brightness camera, this is just for visualization. We're not actually using it, but you hardly see anything in the brightness stream because it's low light, it's fast movements. Some of the sequences we recorded are actually outdoor at night, but the event camera sees things, right? And in addition, you saw it here, it is able to track super high speed motion, something that you cannot do with a normal gray value camera unless you add an IMU or something, right? But here, just using the event camera, you saw also the baselines, they fail on this sequence, same on the next sequence. And here again, you see how fast we can move things. At some point, we really start shaking the camera, and you can see that over long periods, it tracks very precisely with hardly any drift. And so I think you can see it already from these sequences. This may be a very promising sensor for tracking robots that move very fast, that shake like crazy, and still you can track, right? So do consider, if you're working in robotics, this may be a great potential in these sensors. This is how we recorded them. So, you know, over the years we recorded a lot of data sets, and many people are using these. And what you typically find is you record a data set, and then after it's recorded, the next day you realize you should have recorded something else as well, right? And so here we said, let's just put everything on it, right? So there's 2 gray value cameras, 2 event cameras, IMU, all synchronized, calibrated, timestamped properly, right? So, you know, even if you want, so if you want to do stereo events, you know, there is data that you can use. That was the point, for the community to have all the data to develop methods. Here's examples of the data set. So this contains gray value streams, but also event streams from 2 gray value, 2 event cameras, IMU, all of it is there. And this is how it looks, you know, how the world looks in a gray value camera, this you know. But what's nice is you also see how it looks in an event stream. And at some point, we also obviously go through the slides, right? This is why we have the slides in our building, for developing SLAM systems and evaluating them. So this is what the corridor looks like in a SLAM system, and in the event stream, and here's the slides in the event stream. We did evaluations. This is an evaluation on the Hong Kong data set. I'll skip. This is a summarized evaluation where we evaluated on all existing data sets. And this is a notorious issue. You are familiar with it. You evaluate on 6 data sets, and reviewer number 2 says, oh, but you didn't evaluate on data set number 7, right? And to avoid that, we said, okay, let's just take every data set that is out there, Zurich, Vector Institute, Hong Kong, you name it, our own data set. And what we plot here is orange is where our method outperforms the baseline methods on just pure event. And you see across all data sets, across all sequences, except for maybe 1 or 2 sequences on the Zurich data set, our method outperforms existing data sets. But even more, we showed when is our method number 1, even compared to systems that use additional sensors. Stereo, IMU, you name it, right? And you see in roughly 50% of cases, it's still number 1. Even though we only use one of the sensors. And if it's not number 1, then typically we are number 2. Right? So this is a very powerful algorithm to track an event camera. Coming back to monocular, you can obviously from a single camera not only track the camera, but then you can train networks to generate a full-blown essentially dense reconstruction. This is Felix Wimbauer's monorec, where basically from just a single camera in a car, this is one of the Kitty sequences, we're able to reconstruct a dense world. I don't want to go too much into detail, but one element in the monorec is that there is a component that filters out moving objects. It's we call it mask module. And why is it there? In our first approach, we just didn't model moving objects. And what happens, you can imagine, they get smeared out over the world. It's actually very beautiful. I loved it. But then my students said, Daniel, we don't want smeared out cars in our reconstructions. So they added a module to filter them out. Too bad, right? But now the moving objects are essentially gone. But I'll come back to how to model movement. This was our first effort. We just filtered them out. Everything that moves independently, the module filters it out, and so you get a reconstruction of the static world. This is a very recent work, I should say, and I'm very happy to be presenting it here because it builds up on a lot of the stuff that was developed here in this building, right? This is work that builds up on the Duster, Master frameworks. It's a work that we call VISTA-SLAM, Visual-SLAM with symmetric two-view association, coming up at next year's 3DV. It takes in a video, and then 2 frames, I and J. And if you look at the Duster, there is it's not symmetric. So it predicts the point cloud in the coordinates of one image, And what we wanted is an approach that has a single encoder-decoder for every frame, and that is by construction symmetric. And so we predict the movement from I to J, but also from J to I. And the nice thing is that then everything is formalized in the frames of, in the coordinates of frame I and in the coordinates of frame J. We have a single architecture with shared weights, so actually the number of parameters is much lower. It's like 30% lower compared to the Duster approach. And in addition, since we're working in the coordinates of each frame, we can then run a pose graph optimization to get global consistency. And so for us, the nice thing about the VISTA-SLAM, it's a very lean framework to combine a learning-based front end with a global optimization back end. And what it gives you is, in some sense, all the benefits you'd want from a monocular SLAM system. It gives you large-scale consistent reconstructions because of the pose graph optimization makes everything, and loop closuring in the back end that makes everything globally consistent. And in the front end, you have a fairly lean neural network that predicts point clouds and relative motion between pairs of frames. And again, the advantage of this, symmetric architecture is that you use a single decoder branch instead of dual decoders, and it's significantly fewer parameters. As I said, 30% is actually 35% less parameters. That means it's more lean, more low memory, faster, right? And so it gives you a lightweight and real-time performance. I say real-time, it runs at almost 80 frames a second and gives you large-scale, dense, here's, I think, some example sequences that you see here. So this is on all sorts of different data sets, ScanNet, bundle fusion, 7 scenes, RGBD, TUM RGBD. And for me, this is a nice work. Also, historically, because back more than a decade ago, in 2013, we introduced these, or 2012, we introduced the RGBD data set, and we're working on large-scale, dense reconstruction from depth sensing cameras. And they gave this quality of reconstruction in real time, in 2013 ICCV, for example. And back then I realized this is really nice, but everyone knows these depth sensing cameras, they have limitations. They have range limitations, they can't work outdoors, they're pretty big and power consuming. And I said there must be a way to get similar reconstructions in real time with a monocular camera. And now, more than a decade later, I think we are at that level where we get similar quality, dense, high resolution, large scale reconstructions at 80 frames a second. So if you're interested, check out this work. I think it really tries to combine all the strengths of learning-based and classical optimization techniques into a lean, efficient, and scalable approach. Here's an evaluation. This is on the 7 scenes data set, and you can see that both in terms of camera trajectory accuracy and in terms of reconstruction accuracy, it outperforms the baselines. I should say this is not necessarily the case for all the data sets out there. We found that the performance of different methods varies across the data sets, so this is just a glimpse on one of these data sets. And since this is the right audience and all the leading researchers are here, or many of them people who did muster and duster and also people who did VGGT, right? There are some differences. For example, the muster approach that we saw demoed here is very powerful, but it compares to all the history of the past frames to the incoming frame, and so the computational cost of doing this grows linearly with the lengths of the sequence. Whereas in our case, global consistency comes in through the post-graph optimization that is very lean and real-time. And we did post-graph optimization in the RGBD scanning in 2013, and that was easily real-time even back then. I think we actually introduced the post-graph optimization to Visual-SLAM, if I'm not mistaken. And so here we're using it because it's very fast. Also, if you compare, there's Cuter, for example, or is it called Cutter? Cutter or Cuter? I keep forgetting. Every time I see it, I can't remember how it's pronounced. Really nice work, but it uses a fixed state vector to store history, right? And it has forgetting issues, and it would drift once you get longer sequences. And this, to some extent, is also the case for VGGT. VGGT stitches multi-view submaps, and so that likely creates longer drifts when the sequences get longer. In addition, the VGGT, it uses a much heavier front end, right? It typically uses 16 or 32 views. Here, we only use a front end that always uses 2 views only. So it's very lightweight. That gives you real-time 80 frames a second performance on these videos. So this is trying to highlight a little bit how our approach, the VISTA-SLAM, differs from these baselines. I want to briefly come to this part. This is dynamic reconstruction. I'll go a little bit quicker because I'm seeing I'm running out of time. This is, you know, going further to capture dynamic, casual videos of dynamic scenes. There is a lot of work there. You know, the monster, for example, the Mega Sam, the Cuter, the Aligner. And they're very impressive in terms of the results, but they're all supervised. So you need training, you need data collection, you have data sets, but then once you train on these, you will have data set biases, and then if you simulate the training data, you will have a sim to real gap. So supervised approaches have all of these drawbacks, and they're well known. And so what we advocated also this year at CVPR is this work called Anycam that does the same, but in an unsupervised way. So in goes a casual video, as you see on the left. Then we have off-the-shelf modules that predict depths and flow. And then all of this gets fed into a self-supervised module, Anycam, to generate the relative motion, the camera motion, the intrinsics, uncertainties, and as you can see, a dynamic reconstruction here. And so the benefit is that this is unsupervised, and then here's another example. Sorry, I should actually play the video. Here you see how it can determine in a feed-forward network the movement of the camera in a dynamic scene. I'll go a little faster here. This is a more recent work by Wei-Rong Chen. Back on Track, it was at ICCV a few weeks back. Here it tackles a similar problem, but the idea is to generalize bundle adjustment to dynamic scenes. And as you know, bundle adjustment is this classical approach to reconstruct camera movement and 3D structure in a globally consistent way, but it assumes static scenes, and it was bound to static scenes until now. And what we do in this work is that basically we say the movement that you see in the video is a superposition of the camera-induced movement and the object-induced movement. And then we train a neural network to tell us what is the object movement. And then basically we can subtract that object movement and essentially warp the sequences to remove the object-induced movement. And then we can apply bundle adjustment on the residual, on the remaining movement. And that way we are able to extend bundle adjustment and get accurate reconstructions of the camera movement and the static background that actually not only filter out the moving object, but actually use the moving object, but just correct for its motion before running bundle adjustment. Dynamic scenes, maybe one more work here. This is going more in the direction of generative AI. So this is how far can you actually reconstruct dynamic scenes like this moving cat from just 2 photographs. That's all. I give you 2 photographs, a cat at time 1, cat at time 2. And this system, you can see it can recover a 3D cat that moves. So there is a very powerful generative AI tool that does 3D, and then we model the movement of 3D. And this is work by Lu Sang and collaborators, also appearing at 3DV next year. So just given 2 images, we can of a golf player here in 2 different poses, we can create a whole video of a 3D golf player. Here you see the image, and here you see the 3D reconstruction it generates and the move. So it's a moving 3D shape. So it's 4D reconstruction from just 2 images. Here's the same. This is the input image. This is the horse it generates, and it models a deforming horse from just 2 photographs. And I find that amazing how we can use generative AI and computer vision to generate dynamic worlds from very little data. This is very last work. I'm really running out of time. This is a startup that we created to track the dynamics in the world. The way it proceeds, maybe to show you this, is we take a drone. We map the 3D world from the drone. And then we can use drone videos. Why do we reconstruct the 3D world? Because we want to track traffic, and the traffic must be grounded to be maximally precise. So we get centimeter precision in the tracking, 3D tracking, but what's important is to have an accurate model of the ground plane to track it on. And then we can track traffic, as you can see here, hundreds and hundreds of cars that we can track for hours. Why do we do that? We want to understand how humans behave. This is what I started with. How do humans behave in traffic? And then we can use that data to create simulated worlds where every agent in the simulation is mapped on a real human being. And I think this data is very important to also develop reactive agents, to understand how people behave, how they interact in traffic, you know, between cars, cyclists, pedestrians, etc. And this is a very complex interaction. We all know that. And then, you know, we want to understand how accidents happen. Here's an example of an accident. We see lots of accidents. If we film at the right intersections, we can see, you know, regularly accidents. And that we provide this data, for example, to train reactive agents. We work with many companies in this field who are interested in having that data to develop their own models of human behavior. So you see, we're engaged in a lot of startups. This is the very latest startup, a company called SE3 Lab that I co-founded with two of my students, Lukas Köstler and Simon Klenk. They are, by the way, the guys who did the Devo. And they decided to do this startup, and it's working really well. It's a startup on spatial AI, autonomous systems, autonomous drones. So I think I'm talking to the right audience here. If you're looking for the next step for your career, be it, you know, a full-time employee, be it an internship, we can offer very attractive internships in this startup. Just reach out to me or scan the QR code, and we're happy to see if we can offer you something attractive. So we're very much looking for talents. The company is growing at an amazing speed. So please join. It's an exciting time. So I summarize, I talked about my beginnings in autonomous systems, autonomous robots, autonomous cars, autonomous drones back in 2005. And then I talked about SLAM, dense and direct SLAM, deep SLAM. I talked about dense reconstruction with deep networks. And then I mentioned this VISTA-SLAM that combines in a, I find, very beautiful way, learning-based formulations with classical optimization. Then I talked about dynamic reconstruction, both the things like the Anycam approach and also reconstructions of traffic. I always want to say human trafficking, but I think that's not the right term. It's you know, how humans behave in traffic. That's it. Thank you very much for your attention.